So in this video, I'm going to use Cardano's formula to write a Python function to calculate the specific volumes given P and T for the SRK equation of state. So to start this, what we're trying to do is get these roots from our cubic equation that we derived before. So to start, I'm going to just define a function here for Cardano. And what we're trying to get are these A, B, and C values. So A, B, and C. And to start, we first need to compute these Q and R values. So I'm going to put in those equations. So Q equals, it is A squared, A squared minus 3 times B divided by 9. And then R equals, it's 2A to the third, and I'm going to put that in parentheses, 2A to the third minus 9 times A times B, and then plus 27 times C, and all that gets divided by 54. So now we want to find the roots here. And to start off, we know that Q and R are real because our A, B, and C are real. So when R squared is less than Q cubed, then the cubic equation has 3 real roots. So I'm going to start off with this situation. So if R squared is less than R squared is less than Q cubed, then theta equals numpy arc cosine of R over Q to the 1.5. And then our roots equal these formulas right here. So our roots, and we can just make this an array of the roots. So equal -2 times Q to the 1/2 times cosine of theta over 3 theta plus 2 times pi over 3 and theta minus 2 times pi over 3. And then all of these are minus a over 3 as well. So minus a over 3. And then what we're going to want to return is our roots. But I'm also going to sort them so that we have them from smallest to largest for the future. And looks like I forgot a multiplication right here. So now that we have this, we need our other situation where if r squared is not less than q cubed, and that will be this situation here. So a will equal, and this is just getting the sign of r, so that's not the trigonometry sign, it's just getting if it is positive or negative. So to do that, we just use a numpy formula, numpy sign, and this is also negative of the sign of r times the absolute value of r plus r squared minus q cubed all to the 1/2. And then all that to the 1/3 as well. I think that is correct, yes. And then for b, it is different when a equals 0 and when a does not equal 0. So we're going to need to define that as well. So b equals 0 if a is equal to 0. Every other case, when it's not equal to 0, it equals q over a. And then for this, we are going to want to return our roots, which are a plus b minus a over 3. A plus b minus a over 3. So now we can actually use this to get our volumes. So we're going to do that by using the equation that we derived before here with our compressibility factor and get the roots of that in order to solve for the volumes. So first I'm going to define a function for the volumes, and again we will be entering a pressure and a temperature, and then we're going to need our A, B, epsilon, and sigma values from before up here. So that's our A, B, epsilon, and sigma from our cubic ABS, and we are also going to need to define Z, our compressibility factor, and that's where this will come in our derived equation. So I'm going to start typing that in as well. Z equals card of negative beta plus E times beta plus sigma times beta minus 1. And then negative epsilon times beta squared beta squared minus sigma beta squared plus epsilon times sigma times beta squared minus epsilon times beta plus it will be plus minus epsilon times beta minus sigma times beta plus Q times beta and then finally our negative epsilon times sigma times beta cubed minus epsilon times sigma times beta squared minus Q times beta squared. Just make sure that these parentheses line up. Yeah. This parenthesis there, that parenthesis, that parenthesis. Yep. Yeah. That lines up there. Alright, and then now we need to define our beta, which beta will equal, from our derivations before, it equals b times p over r times temperature. And then we also need to find Q from before, which we defined as A over B times R times the temperature. And then what we want to return here is the volume, so we're going to return, and we know that the volumes from our compressibility factor equation is equal to the compressibility factor times R times T all over P. And now finally, I'm just going to test it and make sure that we get our volumes 1e to the 7th. And let's try like 600. So there we go. These would be our 3 roots for our answer.